want to talk about reflection today. Now, as I thought about this topic a lot, and yes, Roni, I did reflect upon it. Horrible joke. On this topic, you kind of know it. You kind of understand this already. It's mirrors. It's how mirrors work to some extent. But you really haven't thought about it probably too much in a scientific manner, in a predictive sort of manner. The Ray model works very good. You can go kind of deep into this. We're not going to go that deep in class. But I want to talk about initially, when you do reflection, most of you guys like to think of reflection just as, mirror type reflection. But that's not reality. Light reflects differently. There's actually two types of reflections. There's specular reflection, and then there is diffuse reflection. A specular reflection, mirror-like. Examples, natural examples of reflection. How would you make a mirror, 2,000 years ago? How could you check to see if your hair was in place? How could you check stuff like that? Well, you can polish metal. So you got polished metal was one of the things, but doing polished metal to do that and getting it nice and flat, it's difficult. You can do it with polished metal. Of course, water, when it's still, acts as a very nice reflector. Now, it doesn't reflect all the light. It only reflects about, well, it depends on the angle, 5–10% of it or something. But if you go up, the ocean doesn't look too much like a reflector, but if you go up to like a glacier lake, I've seen some glacier-made lakes where it kind of goes into the lake and it just kind of sits there. Water doesn't flow out that much. These glacier lakes are just creepy calm. And there's very little wind. Man, it looks like a mirror image of, say, the mountains behind it. I've been up to the Icefields Parkway up in Canada. And if you go down there and see some of those lakes formed by those glaciers, it's beautiful. It's amazing. The mirror-like quality of that surface of the lake, especially, when you're looking at an angle to it. Not a real steep angle, but closer to what we call grazing incidence, or a very low angle to it. It's just, you see the mountains and you see like a reflection on the water of them. You can see it like on fishing ponds sometimes if you go there on a really calm day. It's really cool. It's really cool with that. So I'll say mirror-like polished metal, lakes, ponds. Now, mirrors, how do we get these mirrors today? Actually, what we do is we basically take a piece of glass, get it nice and flat, and then we basically coat the back end of that glass with a really thin coating of aluminum, and then you just put a protecting coating on the back side of it. If you go on YouTube, there's some stuff on how to make mirrors with some aluminum slurry and stuff like that. It's not that hard to do. So most of our mirrors are glass with aluminum coating. And I will put this here, they are back surface mirrors. Most of the mirrors you deal with are back surface. In other words, you've got the glass, then the aluminum coating, and then light will go into the glass, hit the coating, come back off, back through the glass, and back out in the air. That's how mirrors work to some extent with that. If you want to get rid of the effect of the glass, you can make what we call front surface mirrors. It's like where you put the coating on it and just the aluminum coating, and don't use the side, don't put a backing on it, just kind of flip it over and use that side when you put the coating. You can do that. Those, of course, if it gets scratched any at all, hey, you can see it really well. That's more of a research thing using front surface mirrors. Now, one thing we can say about this, if it's specular reflection, we'll say that when light comes in, it goes back out just the same. And what we'll say is, with respect to the normal, with respect to the normal. Now you could do it the other way, but we're going to do this with respect to the normal because of things going forward with the model. With respect to the normal, the incident angle equals the reflected angle. So we'll say here that angle of incidence equals angle of reflection. Or theta I equals theta R. Angle of incidence equals angle of reflection. That is specular reflection. And for mirrors, that's the way they work. That's the way they work. Now, diffuse reflectors, they're not like that. They're rougher surfaces. Okay, rougher surfaces. You could say this whiteboard. Unless you get, I mean, you can see a little bit there, but it's hard to really see a good image. Paper, it's definitely a diffuse reflector. Metal, unpolished. Pavement on a road. These are all carpet. I can keep going on. These are all diffuse reflectors. And what we think of with those is, it's not, who knows how it's looking like. We'll say it looks something like that. So this one will come in at a certain angle of reflection. Then this one here will come in and maybe do like that. And then you've got another one that comes in, say right here, and it goes out that way. So here they're about the same. Here the angle of reflection is much, much bigger with respect to the normal. It goes out almost straight. Here the angle of reflection is much, much smaller compared to the incident angle. Because these hills and valleys you can think of it as, and this is nice flat plane. Here when it hits, now this is valid at the point. But because this changes, it's not constant. Now, if this was a constant, say, angled surface, it would work. But here you got an angle down, here you got an angle flat, here you got an angle up a little bit. Because these angles are all different, you don't get specular reflection. It's diffuse. It spreads out. So with diffuse reflectors, I'll say you don't see an image. And diffuse reflectors, to predict what it gives you, I mean, the math is horrendous. I mean, PhD level stuff. I will tell you though, when you polish something, everything at a point looks like this if you measure to a certain point, to a certain high resolution. There was a company in Charlotte, a buddy of mine used to work for, I used to work with him, and you can actually, it was using they checked computer wafers, and they actually had a machine to look at light would shine onto it, and how much light would shine onto it, and how much was specular reflected, and how much was diffusely reflected. And based on, because they had a little camera that would kind of go across like this and find all the angles and how much light is at each angle on the as it came in. Most of it here when it was specular, but you had some diffuse stuff like way back here actually would come back at it a little bit. And based on that, they could tell you the flatness, the profile of that wafer to really, really high precision. Funny thing was, the mathematics of it was extremely difficult. There was a couple Russian guys, if I remember correctly, I was told that basically had to come in for the math. It's not stereotypical, but it's a lot of these guys that were Russian were very good mathematically, and they knew the optics and the math of it. I've done some math, not at that level, it's statistical stuff added on it too, but a really cool machine. Company ended up getting bought out. Was going out of business, got bought out by someone else or something. But you can use this idea of specular and diffuse reflection to actually measure surfaces. And these were hundreds of thousands of dollars of instrumentation. These instruments, they made, hundreds of thousands of dollars each. And you make computer wafers, computer chips, the flatness and other properties of how flat that wafer is really makes a difference in your outcomes that you get for quality of chips, trash, and stuff like that. So those are the specular and diffuse reflections. We'll look at plane mirrors in a minute. Right now, I'm going to erase this. Let's look at plane mirrors. When I talk about plane mirrors, I'm not talking about non-fancy mirrors. No, this is plane. Plane meaning it acts as a plane, not P-L-A-I-N, but P-L-A-N-E mirrors. So a plane mirror, you draw something like this, and you put this on the back side, so you say, all right, that's where it's attached. Light can't go through it. This is the back side of it, where light doesn't get light reflected off of it. So let's put a person right here. Okay, there's our person. Who are we going to make that be? Who are we going to make that be? Frito? Is that going to be you? I don't care if you don't want it to be you. We're going to call this Frito, okay? This is Frito today. Alright? And so Frito is here. And we're going to have someone else. Let's put Angel, you're looking in the mirror here. Here's your eye. Okay. It's the eye of Agamotto or Agamotto or whatever from Doctor Strange. Now, we can do it from Lord of the Rings, the all-seeing eye. We'll do that. We'll make this. So she's doing like Lord of the Rings, and this is the eye looking for her. But the eye can't turn, it can only look in the mirror. So, what he sees is light coming from her. Now, when he sees her from this, what he's going to do is, light's going to come like from her head, hit here. And that's going to come to her. So it's going to come like this, and like from her feet. It's got to get to his eye here. And let's say from her hand. Something like that. Now, let's now this is the eye. Even though it's a, Lord of the Rings eye and, everything that basic physics still holds. So if it comes in this way, the eye, the all-seeing eye there, it's going to extend the light rays out. So what this all-seeing eye sees is an image. Get this straight. A Frito, and Frito's not happy because all-seeing eye is watching her. It forms an image back behind here. It actually forms an image back behind there. So what we have with plane mirrors, the book does a better detail. I know some video and it's hard to see and stuff. What I will say is that this image distance here, we'll call this DI for image distance. This is DO for object distance. And we'll say that the image distance equals the object distance. Or we can say that the image is the same distance behind the mirror as the object is in front of the mirror. So Frida looks like if she's 10 feet in front of the mirror, she looks like she's 10 feet behind the mirror. Now here's the cool part with this. The all-seeing eye here. You know, the evil that is the all-seeing eye. If he doesn't know a mirror's there, he actually thinks Frida is right here. If he decides to rain fire at this point, oh, I'm sorry, I mixed novels and universities. I'm sorry, no rain fire. If he decides to have a dragon come down, the dragons are gone. If he decides to do something right here at Frida, come straight out, that's where he thinks she is. She appears to be right there, but she's really not. Because he doesn't know that mirror is there. Doesn't know that mirror is there. Could this be in the mirror reality? I'm sorry, that's mixing universes again. But this mirror itself, go back to some seriousness, the mirror itself, she appears behind the mirror. When you look at yourself in the mirror, and you know, let's see, who said it? When Irving's back there doing his hair, he's got the girlfriend and everything, he's checking. Are you sure he's looking good? You know, he's flexing in front of that mirror. No, you do that, Irving. But Irving's flexing in front of that mirror, getting ready for that date. If he's 1 foot in front of the mirror, he looks like he's a foot behind the mirror. And if you notice, you get closer to a mirror, you look bigger. If you look further away, so, you know, this is a little disgusting, guys, but if you want to pop the zits, I know you guys do that. So you got to get really close, so it looks like you're seeing your own face, but a lot closer on it, so you can see it. But then you got to, if you back off, you can't see it as much, right? That's why you get closer. You want to see the image of you. Looks like you know, only if you're 6 inches away, you look like you're 6 inches behind. So you're seeing yourself 6 and 6. 1 foot away of what you would look like. That's reflection, the way images are formed. Now, this angle of incidence equals angle reflection. You saw I used it here. There's an example in your book, example 34.1. Now, example 34.1 basically has a mirror. And it says, hey, we got a light bulb here. And this light bulb, light from it hits here, and it goes over there, and light from it's here. And basically there's say a wall or a floor here or something. What happens, this light from this light bulb gets streaked out. And it basically says if we know the distance here, we'll say that's 1.0 meters. We know the distance here is 0.50 meters. The length of that mirror is 1.50 meters. And that this is 0.50 meters on the ground. The question is, how long is that streak of light there? You're like, how the heck darn do I do that? Well, let's look at this. We know angle of incidence is angle reflection. So, based off the normal, that's our angle here. Well, that's our angle there. Let's look at this. We know from geometry, hopefully you remember from geometry, alternate interior angles. Well, that angle is going to equal that angle. And we know that side's 1.5 and that side's 0.50. So that we'll say the angle of incidence for the top. Well, we got opposites, assuming an adjacent side and an opposite side. So what trigonometric function? So we're going to do angles, and we got triangles, and we got sides, so we know we're probably going to use trig. What trig function involves opposite and adjacent? No, it's not sine, Nick. It's not cosine, Nick. What's the only one left, Nick? Tangent. Very good. It's tangent. So we're going to say the tangent of this angle theta is going to be equal, in this case, opposite over adjacent, 0.50 meters over 1.0 meters. Well, I'll let you do the math to find what that is. Okay. Let's look down here. Well, down here's the same way. Angle of incidence is angle of incidence here. So we're going to say the tangent of theta incidence for the bottom, and we're going to say that's equal to, now it's this whole length here, now our triangle is across, down, and there's hypotenuse. The ray is the hypotenuse of that triangle. Well, it's going to be this total distance, which is 2.0 meters over, that's the opposite side, adjacent 1.0 meters. And you can find theta from that. Well, what's cool is if you know this theta, do you know that one? Well, yes you do. And if you know that one, you can find this one here. And we know these, since that's bisects, that those are equal. That's just going to be 90 less than that, this one here. And 90 less than that? Well, let's see. We've got a distance down. We've got a length across. So we can find that total distance there. Once you find this total distance, you can find this distance right here. And if you know this distance, that total distance, subtract them. And you can find what you're looking for. A little bit of geometry. Some of you, that's a bad word. But you got to know it. This is really geometry stuff. If you like geometry, this ray optic stuff really is geometry based. It really, truly is. They do another example about height of a mirror. That one's honestly pretty darn intuitive. But this one I didn't think was. This was it's geometry and trig problem. Remember I've talked about it. You got to know the trig. You got to know the trig. And so that's a little bit example on reflection. Okay. Now I want you guys to think very hard on this. I want you to reflect upon what I've talked about. And we will try to bend your ideas or refract them in the next lecture.